Let's start with the U substitution trigonometric integrals. First, you want to make sure that the functions are within a pair. It's very, very important. Then you observe the parity of the exponents. Which functions can go into the du, so what left can be expressed as a function of u without radicals. Radicals are very, very difficult, so you don't want to have radicals when you integrate functions. And then you want to try your choice of u. If it doesn't work, change it to be the other function. Why I'm saying the other function? Because we are working within a pair. So after your integrand is a closed pair, then you have only two choices for the u. Is one of those in the pair? Still doesn't work? Maybe you have to use other technique of integration. Let's start with an example of the pair sine and cosine. We have to integrate sine x to the power of 5, this is an odd exponent, times cosine x to the power of 2, which is even exponent, dx. The truth is that most trigonometric integrals are just a sophisticated U substitution. In the U substitution, we looked at the composite function and we took the inner function to be the u. Here we cannot do it because if you look at this, for example, it's a product of two functions and each of them is composite. So the u can be cosine x or it can be sine x. What I should put in the du, so the leftover will have only even exponents, because I love even exponents. When I have even exponents, I can use the Pythagorean identity to write the sine as cosine or the cosine as the sine without using any radicals. So in this case, I will definitely would like to take the du to be sine x dx. Let's not do exactly the same, but now with a combination of the Pythagorean pair, which is tangent x and secant x. What happens when m is odd? If m is odd, I can take the du to be tangent x, but I cannot just have tangent x dx. I need tangent x secant x dx. Because this is the du when u is secant x. And then what I have now is that the exponent of the tangent x is now even, because I took one of the exponents into the du. So now I'm ready to express tangent to the power of 2x as u to the power of 2 or secant to the power of 2x minus 1. What happens when n is even? Then the du is going to be secant to the power of 2x dx. It means that by doing so, after I've taken 2 from the exponent for the du, the exponent of the secant x is still even, because even minus 2 is an even number. So in this case, u is tangent x, and I have to use this Pythagorean identity that secant to the power of 2x equals tangent to the power of 2x, or u to the power of 2 plus 1. But here is a big troublemaker, so I will put a question mark here, okay? To understand that, let's see. First of all, let's start with the case that n is odd. If n is odd and m is even, then if I will take secant to the power of 2x dx, then the exponent of the secant x is still going to be odd, which is bad because I cannot take the other one. I cannot take the other du to be secant x tangent x dx because the exponent of the tangent is even, so if I take one exponent out of that, it is odd. So let's do example of the nice case for which we have 3 for the exponents of tangent x, and 4 for the exponent of secant x dx. Because secant x is with exponent which is even, I can take du to be secant to the power of 2x dx. And then the u obviously has to be tangent x. So now again, I'm writing this, I'm splitting everything up so I can really translate everything to you without mistake. So I break down the secant to the 4x dx to be secant to the power of 2x times secant to the power of 2x dx. Now let's see. This one is tangent to the power of 2x plus 1, which is u to the power of 2 plus 1. The tangent can be in any exponent because this is the u, and the secant to the power of 2x dx is d of u. So again, we're getting a polynomial of u, very easy to integrate, and now we have to substitute back tangent x for the u, and we get that. And now we are going to do it again in a different way, because the exponent of the tangent x is odd. So I can also take du to be tangent x secant x dx. And now u is secant x. So now I'm splitting the exponent of the tangent. So I get tangent to the power of 2x and then tangent x, but also I have to split the secant to the power of 4x to secant cubed x and secant x, because one of each of the exponent of the tangent and the secants are now going to be swallowed into the du. Okay, so now the only thing is I need to express the tangent to the power of 2 as a function of the secants without radicals. That's the whole idea. And I get secant to the power of 2x minus 1, which is u to the power of 2 minus 1. So I get that. Now again, just distribute, and we can take the antiderivative. It's just a simple polynomial, and we are substituting the secant x for the u, and we get that. Well, before I got this one, and now I'm getting this one. Is it really a big question mark? No, it's not. Please, I always tell my students, do not get crazy if you do trigonometric integration and you don't get exactly what is written in the end of the book as an answer. Because of the flexibility of the trigonometric identities and functions, many times you do everything right and you still get an answer which is not exactly written in the end of the book. For example, here I got really different answers. Well, both of them are good. Now I'm going to do it even in another way. Let's say that I'm doing something and it's really complicated and I'm really have no idea what to do. It's always worth it to try to write everything as sine and cosine. So in this case, I will get that. Now it's pretty obvious that because the cosine is in the denominator, that u have to be the cosine. I don't have much choices here. So if the u is the cosine x, then d of u is negative sine x dx, which is nice because by taking one of the exponents of the sine cubed of x, I can split it now to sine x and sine to the power of 2x. Nice, because it's an even exponent, so I really like it now. Okay, so the only thing again is sine to the power of 2x, and we know that this is 1 minus cosine to the power of 2x, which is 1 minus u to the power of 2. And I get that. Because I have one amount in the denominator, I can just divide 1 by u to the 7 and u to the 2 and u to the 7, and I get that. Again, easy integration. Okay, this is what I get. And now we're going to write cosine. And we get that. Okay, why not to express it as this one? This is familiar, isn't it? because 1 over cosine is just the secant, okay? So 1 over cosine to the power of 6 of x is a secant to the power of 6 of x, and 1 over cosine to the power of 4 of x is secant to the power of 4 of x. I got this, and I got this, I got twice this guy, and I got once this guy. So let's summarize this example. We got two answers that are written really differently, even though if you will check each one of them, you're going to get back your integrand after differentiating, so it means that both of them are right. If you get secants to the power of 2x as an answer plus c, then it's exactly the same as to get tangent to the power of 2x plus c, because the difference between secants to the power of 2x and tangent to the power of 2x is actually just a constant.